Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about the Seamaphores, that is also a software-based solution to the critical section problem. How to use and implement that Seamaphores to solve the problem. As we know that mutex locks provide the simplest software tool to address to the critical section problem, now we will talk about a robust tool that will take all the advantages of the mutex locks and also provide a sophisticated way to design the protocol to address to the critical section problem. Now we will talk about a semaphore S, which is an integer variable which that can be initialized to 0 or 1 or maybe some other values to actually control to the access to the shared data or access to the critical section. Now, apart from the initialization of this integer variable S, only two atomic operations known as wait and signal can access this variable in the critical sections. Now we will define this wait and signal operations, which was previously and originally termed as P, which is the form of test, and signal was termed as V, which in the form of increment. So now we will define these two operations. This is the basic definition of an wait operation of a semaphore. Here the semaphore is designed and initialized with the number of resources. If it is 0, then it should busy wait with the processes. Otherwise, it should decrement the value that it has resource used. The next operation is the signal operation. Here we are only signaling that the resource have been used and deallocated to make it used by the other processes. Now this wait and signal operation must be performed atomically, and the semaphore modification value by this wait and signal operation must be done indivisibly. That is, no two processes can access and modify these two semaphore values, including this wait and signal operation with different other operations. And the other general condition that S is less than equals to 0 checking and the decrementing of S will be done indivisibly too. That is, without any interrupt, it should be done. Now, operating system distinguish between two types of semaphores known as counting semaphores and binary semaphores. Counting semaphores can range from any the unrestricted domain, and binary semaphores only range between 0 and 1. Thus, binary semaphores works as same as a mutex lock. Even some system which cannot provide mutex locks has binary semaphores to provide mutual exclusion in the critical section problem. Now, in the case of counting semaphores, we initialize the semaphore value with the number of resources solved in this problem. Now, in this counting semaphore problem, we want to control the access to the question in resources that have many instances of it to be done with the many processes. Now, as we have initialized the semaphore value with the number of resources available, when our process performs the wait operation and if the resource is available, then it is consumed by the process and S is decremented, so indicating that one process resources has been consumed. And while the process is signaling by call the signal, then it is actually deallocating that resource to other process use that resource by actually incrementing the resource value. Now, if the process number and the semaphore value of integer S becomes negative or 0, then it is identifying that no resources are available in this system. Now, if no resources are available, then a process which is want to use the resources is blocked until some resources are available to the semaphore value. We can also use this semaphore to vary a synchronization problem. Suppose that two processes P1 with statement S1 and P2 with statement S2 order in execution simultaneously in the particular order that S2 should be executed only after S1 has performed its operation. So we can literally done this with sharing a common semaphore sink with process P1 and P2. Thus process P1 will give the command because sync is initialized to 0, P2 will execute only after P1 as P1 is executing the signal statement within the semaphore sync after executing the S1 statement. So after executing the S1 statement, it is releasing the semaphore to get used by the process P2. Now process P2 acquires permission for this use of semaphore, and after that it executes the operation statements S2. So in that way, the ordering that S2 will execute only after S1 is satisfied with the common semaphore sync. Now we will implement this semaphore in the actual process synchronization. As we know that mutex lock suffers from busy waiting. As for the same semaphore S we have described, the wait and signal suffers also from busy waiting. Thus, while waiting for a resource to be available in the wait operation, it is busy waiting and spins itself again and again within that wait operation. To remedy this situation, wait and signal can be modified in this way. When a process is executing an wait operation on some resources and the resource is not available, then rather than busy waiting, the process blocks itself. And the semaphore puts the process blocked into a waiting queue associated with the semaphore. Now, while the process is waiting in the semaphore queue, then other processes can run the CPU allocated by the CPU scheduler. A process which is blocked waiting with the list associated with the semaphore S can restart its execution if some processes operates a signal operation on that semaphore. And that block and signal can use this process resume to resume its operation. The wake up operation calls the process from the waiting state to the ready state. Now the CPU scheduler will decide that it will preempt the running process, or it should newly running process wait for the running process to preempt this execution. To implement the semaphore under this way, we will first define the semaphore. This is the definition of a general semaphore using this operation, where it contains an integer value. Along with that, it is containing a list of processes. When the wait operation is performed on that process, it will be get into the end of the list, and when the signal operation is invoked, then the process will be removed from the list. Now we will define the wait operation of this semaphore. First, with the parameter semaphore S and pointed to it, it is first decrementing that the resource has been used. After that, it is checking that if it is negative, then it is adding the process to the list of processes. And now it is performing the block operation. The block and wake up operation are normal system call operation provided by the kernel. Now the block operation puts the process into a waiting state. In this way, wait is operated on this type of semaphore. Now we will see what happens with the signal operation. Now, as in the signal operation, we are first releasing the resource using the ace value incrementation, and if there are any other process waiting in the list queue, then it is actually removing the process from this list by the wake up operation by putting it in from the waiting state to the ready state. Note that here the semaphore values can go negative as well. In the constructive and traditional semaphore values cannot go negative in any way. Here the negative construction is actually the numerical value of the number of processes waiting in that queue. Now as the processes get removed from that queue, it will eventually reach 0 and then become positive. These facts result from reversing the ordering of decrementing and calling the operation from this signal operation and wait operation. The list of waiting processes can be implemented in the process control block or PCB of the link field of that list. As we know that the semaphore is containing an integer value and a pointer to the list of processes presented in that queue. Now the semaphore contains both the head and tail pointer to that queue. Now for confirming the bounded waiting time period requirement, we can use a FIFO queue to satisfy this operation. As well, any queuing models we can use. Any queuing strategy cannot affect the semaphore performance in any way. The correct usage of semaphore is independent of this queuing strategy. It is critical to that wait and signal operation to be performed atomically. No two operations of processes can execute this wait and signal operation on the same semaphore at the same time. Thus, the race condition must be guaranteed to be restricted that only one process can perform this wait and signal on one semaphore at a time. In a single processor environment, this can be done by simply inhibiting an interrupt. By inhibiting an interrupt, wait and signal can be performed by one process only, because once the inhibiting of interrupt is done, no instructions from different processes cannot be interleaved. Thus, it can be only implemented in a single arcing environment way. Only the currently running process are executed to allow before the interrupt is re-enabled and scheduler can regain the control. In multiprocessor control environment, the scenario is entirely different. Disabling interrupts should be made to every processor because any processes that are running on different processors can be wait and signal performed on the same semaphore at the same time if all interrupts are not disabled on every processor. But disabling interrupts can take huge amount of computation time and also decrease the performance very significantly. So in SMP architecture, rather than using this type of semaphore, we use simple hardware implementation of compare and swap or test and modify functions to actually provide the mutual exclusion. Now we have to minutely carefully note that we have not continuously or completely eliminated the busy waiting from semaphore. We have only moved it from the entry section to the critical section of the application program. And also the busy waiting is limited to the critical section of the wait and signal operation. And the sections are short if properly coded, not more than 10 instructions per code. So the busy waiting is not interrupted because the critical sections are not held all the time. It is held very rarely, and if then it will be very short handling period. Now the program and the scenarios gone in various situations where the critical sections are long, having very lengthy operations. Their busy waiting seem to be very much inefficient. So in this way, Seamaphore can be implemented in many various conditions like synchronizing processes or achieving mutual exclusion, progress and bounded waiting requirements of solving a critical section problem. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.